We have covered all the instructions that make up the bootstrap loader. Now, let's run the program. First, however, we have to place the Absolute Loader program tape into the high-speed paper tape reader. Be sure to check the label on the tape to ensure that you're loading the correct tape. Also, check to see that the leader section of the Absolute Loader tape is positioned over the read head. Having loaded the Absolute Loader tape into the reader, we now start the CPU at the beginning of the Bootstrap Loader program. The starting address of the Bootstrap Loader program for a machine with 4K of memory is 017744. The first instruction of the Bootstrap Loader program moves the address of our input device's CSR into General Purpose Register 1. This address is located at 017776, the last location in the Bootstrap program. The only time this move instruction is executed is during the first pass through the Bootstrap program. On subsequent passes, it is not executed. On the initial pass of the program, we move our address displacement of 352 into General Purpose Register 2. We are now ready to read in our first byte from the Absolute Loader tape. To do this, the Bootstrap Loader must first start the paper tape reader. The paper tape reader is started by incrementing the reader's CSR. Incrementing the CSR sets the enable bit, which initiates read action. The CPU now executes a test byte instruction and a branch if plus instruction. These instructions generate a loop condition. The central processor remains in this loop until there is a byte available in the DVR. When a byte becomes available, the done bit is set in the paper tape reader's CSR. At this time, the CPU exits from the program loop and proceeds to the next instruction. At this point, the high-speed paper tape reader reads in the 351 leader code from the Absolute Loader program. While this leader code is being read in, we continue to loop through our Bootstrap Loader program. Our leader byte of 351 is stored in the reader DVR. This move byte instruction transfers the 351 leader code into the memory location loop +2. The destination address, loop +2, is derived from the address displacement, 352, which is added to the constant called load. Load is defined as 017400. The sum of this addition, 017752, is called loop +2 and is the destination for the data contained in the DVR. Thus, the previous address displacement of 352 is now replaced by a new address displacement of 351. As shown here, the increment instruction now increments the contents of the memory location known as loop +2. Therefore, the contents of memory location 017752 are incremented by 1 from 351 to 352. Our next instruction at location 017774 is an unconditional branch instruction. This instruction returns us back to the point in the program defined as loop. Having branched back to location 017750, we repeat our read and storage sequence. Once again, we transfer our address displacement into General Purpose Register 2. As you remember, the 352 figure was the result of incrementing the tape leader code 351. As we continue reading the 351 leader code, the following sequence keeps repeating or looping. First, we transfer our old address displacement of 352 into General Purpose Register 2. The tape leader 351 is then read and incremented to 352, giving us our new address displacement. We then branch back and the program is repeated. The program continues to loop between memory addresses 017750 and 017774. So far, we've been reading our tape leader code 351. Now let's see what happens when we encounter the first data byte on the tape. The first data byte on the Absolute Loader tape after the 351 leader is a 075. Data byte 075 will be used by the Bootstrap program to define the starting address of the Absolute Loader program. When 075 is read from the tape, it replaces our old address displacement of 352. After this new address displacement is incremented and added to a constant, it tells the processor where the Absolute Loader is to be stored. Now let's look at the instructions necessary to accomplish this. The data in the DBR 075 is moved into memory location loop +2 by the move byte instruction. Therefore, the previous address displacement of 352 is now replaced by a 075. The contents of loop +2, which is the address displacement, is now incremented. Thus, 075 is now replaced by 076. The next instruction causes our Bootstrap Loader program to branch back to the location known as loop. A move instruction located at loop transfers our address displacement of 076 into General Purpose Register 2. The second data byte on the Absolute Loader tape is now read in. It is a 000. We now begin to store the Absolute Loader program in memory, a byte at a time. The second data byte read from the tape is 000. This becomes the low order byte of the first instruction in the Absolute Loader program. A move byte instruction transfers data byte 000 from the high-speed paper tape reader DBR into memory location 017476. This destination address is the result of adding the constant 017400 and the address displacement of 76. We now have half of the first Absolute Loader instruction stored in memory. The Bootstrap Loader now proceeds to the next instruction in the loop. This instruction increments the address displacement stored in General Purpose Register 2 from 076 to 077. This address, as we have seen before, is called loop +2. The second data byte, which is also 000, is now read from the Absolute Loader tape and is stored in memory as the high byte of the first instruction. Thus, we have stored the first instruction of the Absolute Loader program into memory. The Bootstrap Loader continues looping, and the remaining data bytes that make up the Absolute Loader program are stored in successive memory locations. Each word location contains 2 bytes of information or 1 complete instruction. Execution of the Bootstrap program continues until the entire Absolute Loader program has been stored in memory. Notice that the Absolute Loader program occupies a block of memory between locations 017476 and 017752. Notice that the last 4 word addresses of the Absolute Loader program are overlaid with the first 4 word addresses of the Bootstrap Loader program. Let's discuss the significance of these overlaid instructions. As a result of this overlay, part of the original Bootstrap Loader program is modified. This modification causes us to stop execution of the Bootstrap Loader, and instead, the program counter branches into the Absolute Loader program. Now, let's take a closer look at this overlaid area. The overlaid instructions are identical to the original Bootstrap instructions, with the exception of memory location 017752. The contents of this location have been changed from 352 to 373. The value 373, stored at location loop +2, represents a new address displacement. Let's see what effect this address displacement has on our Bootstrap program. The contents of memory location loop +2 are again incremented. The result of 374 is then moved to General Purpose Register 2. Consequently, the destination address of the move byte instruction is changed. The incremented address displacement of 374 is added to the load constant 017400. The result is the address of our branch instruction 017774. The last byte is now read from the Absolute Loader tape. Its contents, 353, are placed in the high-speed paper tape reader DBR. Up until now, we've been transferring our information from the paper tape reader into the Absolute Loader area of memory. The destination for the data now changes. What is this new destination? It's our branch instruction located at the end of the Bootstrap Loader program. The last byte read from the Absolute Loader tape is moved into this location. Thus, our branch instruction offset has been modified from 365 to 353. Let's see where this new offset value directs us. The end result is that we now branch to the Absolute Loader program and restore the Bootstrap Loader program. Thus, The modified branch instruction directs the processor to location 017724. The processor now executes the absolute loader program in order to restore the bootstrap loader program to its original keyed-in condition. To restore the bootstrap program to its original condition, we first execute a move instruction. This move instruction takes the value 352 and places it in memory location 017752. Hence, we have restored the contents of that bootstrap location to its original condition. We then execute a second move instruction. This instruction takes the value 765 and deposits it in another location in our bootstrap loader. This location, 017774, happens to contain our branch instruction. We have thus returned the offset to its original value of 765. The bootstrap loader program is now completely restored and back in its original keyed-in condition. The last instruction in our absolute loader is a jump instruction at location 017740. This jump instruction brings us back to location 017476, where we have stored a halt instruction. The paper tape reader stops reading in the absolute loader program. The absolute loader paper tape can now be removed from the high-speed paper tape reader. The paper tape program you wish to store in memory can now be placed in the high-speed paper tape reader. Some examples of common paper tape programs are the assembler, math package, editor, and the compiler. If our program counter is at location 017500, the continue switch is pressed to initiate execution of the absolute loader program. If the program counter is at location other than 017500, the operator must first key in the starting address of the absolute loader program. Then the operator presses the load address switch and the start switch. This causes the processor to begin executing the absolute loader program. Thus, our absolute loader has taken our paper tape program and transferred it from paper tape into memory. Congratulations. You have now finished the bootstrap loader. Before we wrap up this study unit, let's quickly review program loaders. The bootstrap is manually entered through the switch registers. Its function is to bring in the absolute loader program, which in turn brings in paper tape programs such as the assembler, math package, editor, and compiler. First, we enter the bootstrap loader through the console keyboard. Next, we place the absolute loader program tape into the reader. Then we start the CPU at the beginning of the bootstrap loader program. The bootstrap loader reads the absolute loader tape and stores it into memory. This read operation halts when the entire absolute loader program has been transferred into memory. The bootstrap loader program starts by loading general purpose register 1 with the address of our input device's control and status register. General purpose register 2 is then loaded with an address displacement. Next, the paper tape reader is enabled, allowing it to read in a byte of information. This byte of information is then moved into a memory location. The address displacement is now incremented, and the process continues until we read in the last byte. At this point, the processor branches to the absolute loader program and restores our bootstrap loader. The following sequence of events occurs when we input our program loaders into PDP-11 memory. Step number 1, the bootstrap loader initiates the paper tape reader, thus causing it to read in the leader code from the absolute loader tape. This, in turn, causes the bootstrap program to begin looping. Step number 2, the bootstrap loader transfers the absolute loader into successive locations in memory. Each word location contains 2 bytes of information or 1 complete instruction. As the absolute loader is deposited in memory, it overlaps a portion of the bootstrap program, thus modifying the bootstrap loader. Step number 3, this modification causes the CPU to exit from the bootstrap loader and branch to the absolute loader program. Step number 4, the portion of the absolute loader program that is now executed restores the bootstrap program to its original configuration. Step number 5, after restoring the bootstrap loader, the absolute loader program jumps to a halt instruction and stops. The PDP-11 processor can now use the absolute loader to read in most paper tape programs. Most programs can now be entered into memory just by placing the tape in the high-speed paper tape reader and pressing the Continue button. However, if the program counter is not located at the beginning of our Absolute Loader program, we must enter the Absolute Loader's starting address through the switch registers. Remember, the starting address of the Absolute Loader is dependent on memory size, just as it is with the Bootstrap Loader. Then we press the load address and start switches, letting the Absolute Loader read in our paper tape program. You have just completed a relatively complex unit. Feel free to go back and cover any sections of this unit that you do not understand. We would like you to complete the self-scoring test contained in your workbook. This test is very important and should reinforce your understanding of I/O programming and program loaders.